We come across many objects that follow rotational movements. No matter whether it's a Ferris wheel or a rotating basketball, these rotating objects are a system of particles that considers motion as a whole. So in this video, we will explain what rotational motion is, its types, also the kinetics and dynamics of the system. Rotational motion can be defined as the motion of an object around a circular path in a fixed orbit. It can be divided into three types. The first type is the motion about a fixed axis, also known as pure rotation. This motion describes the rotation of an object around a fixed point, like the rotating of a fan blades or the rotation of hands on a clock, as both rotate about a central fixed point. The second type is a combination of rotational and translational motion. An example is the rolling of wheels on a bicycle. The wheels have two velocities, one as a result of the rotation of wheels and another due to the car's translational motion. The third type is rotation about an axis of rotation. This motion describes objects that rotate about an axis while also rotating around another object. An example is Earth orbiting around the Sun while it also rotates about its own axis. The dynamics for rotational motion are completely analogous to linear or translational dynamics. Many of the equations for the mechanics of rotating objects are similar to the motion equations for linear motion. In this video, we will focus on explaining 5 concepts that will almost cover the basics of dynamics of a rotational motion system. The angular displacement is analogous to the displacement in linear motion. An object rotating about an axis is defined by its angle of rotation, theta. It tells us how much the object has spun. So basically, theta equals s divided by r, where s is the length of arc or distance traveled, and r is the radius of the circle. The unit for theta is the radian. Radians describes angle by essentially telling you how much of the circumference is covered by a given angle. So 180 degree or a half circle worth of angles equals pi radians. And to convert any number of degrees to radians, you just multiply the degree times pi and divide by 180. As many have already guessed, angular velocity is analogous to velocity in translational motion. So we already know that translational velocity is delta d, which is the distance traveled, divided by the delta t, which is time. And in the same way, rotational velocity is a measure of an object's changing angle. Rotational motion can also be periodic, which means it repeats itself after a set amount of time, creating a steady frequency. The frequency is the number of rotations that happen every second. So mathematically, it is 1 divided by the period t. Frequency is measured in rotation or revolution per second, and angular velocity is measured in radians per second. And 1 revolution is equal to the circumference of the circle, which we already explained is 2 pi radians. So in order to convert from frequency to angular velocity, all we need to do is multiply the frequency by 2 pi. But be aware, if you convert from RPM or revolution per minute, you will also need to divide by 60 to get a radians per second. Besides the angular velocity, a rotating object also has a tangential velocity. The relationship between tangential velocity and angular velocity is given by the law V equals omega r. This equation says that tangential speed v is proportional to the distance r. So the further a point on the line is from the pivot, the greater its tangential velocity has to be. But be careful to remember that all of the points along the same line has the same angular velocity because they all cover the same angular distance in the same amount of time. Well, based on what we already discussed till now, you can already guess that angular acceleration is the derivative of angular velocity. It describes how an object's angular velocity is changing over time. As an object rotates, each point on it must accelerate, creating centripetal acceleration. So let's quickly review What is centripetal acceleration? Centripetal acceleration, also known as radial acceleration, is the inward acceleration of any point on a rotating object, and it is equal to the angular velocity squared times the radius. And as we mentioned, in rotational motion, there is always centripetal acceleration. While in contrast, tangential acceleration isn't necessarily present. During uniform circular motion, the tangential acceleration is zero. That makes sense because tangential acceleration describes whether an individual point on a rotating object is speeding up or slowing down. So if the object undergoing uniform circular motion, that means it has a steady velocity, hence no speeding up or slowing down. Like linear velocity, tangential acceleration depends on the distance between the point and the center of the object. So we can say it's equal to the angular acceleration times the radius. And obviously, the rate of change of tangential velocity gives the tangential acceleration. Moment of inertia, also known as the angular mass or rotational inertia, can be defined with respect to the rotation axis as a quantity that decides the amount of torque required for a desired angular acceleration. And as its name says, it's a property of a body due to which it resists angular acceleration. The formula for the moment of inertia is I equals to the summation of the equivalent mass times the radius squared. The moment of inertia depends on the distribution of mass around its own axis of rotation. It varies depending on the position of the axis that is chosen, that is depending on the location and direction of the axis of rotation. The same item might have various moment of inertia values. The moment of inertia is different for every rigid object and also different according to the axis, so it is easier to memorize the law of common rigid objects. You can find it by typing moments of inertia for different objects on the Google search bar. Though there are still a couple of theorems you need to be familiar with. One of them is the barrel axis theorem. The barrel axis theorem states that the moment of inertia at any point parallel to the center equals the moment of inertia at the center of mass plus the equivalent mass times the lever arm squared. This rule can be handy in solving many problems. Torque is the angular version of force. For example, we apply torque to operate a merry-go-round. Force is generally applied on the lever arm to rotate an object about its axis. Mathematically, torque is given by the following equation: tau equals r f cosine theta, where tau is the torque, f is the force applied, r is the distance of the applied force from the rotation axis or the length of the lever arm, and theta is the angle of rotation. The unit for torque is Newton meter. The torque is greatest when the applied force is perpendicular to the lever arm. Newton's second law of rotational motion states that every object will move with a constant angular velocity unless acted upon by a torque. When a torque is applied, the object changes its angular velocity and gains angular acceleration. The further the force is from the rotation axis, the higher the torque and the angular acceleration. Similarly, the larger the torque, the higher the angular acceleration. On the other hand, the more massive the object is, the slower it accelerates for the same torque applied. And by that, I can say congratulations. Now you have learned the basics of rotational motion system. So let's all thank God that we have reached here. This episode is created by Minna Sharif, Dua Ayman and Fatma Khalid. For any further explanation, please don't hesitate to contact us.